Good morning, everyone. As I said last time, this will be our last lecture in the summer. So we can begin today. And let me know if my volume is too low or sound is too small, but those two are mean the same thing. So I don't know myself, but last time someone said like your voice is too low, but you can let me know so I can adjust it. All right. So today, let's talk about our last concept in the basic of probability, which is called the central limit theorem. So last time we have already saw the weak law of large numbers, which means like if we increase the sample size, if we increase the n to be very large, and the expected value of the average, well, very, very close to its mean, right? To its close to the real mean. And well, just in the range of epsilon about it, and epsilon can be close to zero. So that's our finding. But someone may ask a very interesting question. What about its variance? How does the variance behave when the sample size increases very much or the n increases very much? Is the variance stabilized? Does it vanish out or it just distribute very flat and doesn't have any meaning? So let's find out today. And this time we'll give credit to the Alexander Giesing. Now he's in National University of Singapore, or previously University of Washington's Department of Statistics. We'll use his material to conduct some interesting examples. Right. So yeah, so we'll go through the central limit theorem today. And so first, let's talk about a very interesting thing is the gamma distribution. So gamma distribution we have not really talked about before, right? So gamma distribution or gamma process, as you can search on the Wikipedia, is based on the exponential distribution. So it's a formula based on exponential distribution, and it's built up to calculate like how many times an event will occur during a center time range, a time duration from time 0 to time t. So that's its definition. It's always depicted by gamma. So it's called gamma process. And also, just like gamma distribution is defined on the exponential distribution, there's another distribution which is based on gamma distribution, which is called the beta distribution. Okay, but that is beyond our scope. But probably we'll see that in our next summer or next winter as we study more advanced probability. Okay, so this example we'll see how the average of the gamma distribution with the parameter 2, 1 behave when the sample size n goes to very large number. All right, so x1, x2, x3, xn, they are identically independent distribution, which means they are all gamma to 1. And we can see like it is given the density. This is the gamma distribution's density for each xi, and I here is for every like 1, 2, 3 to n, right? So the PDF is here, and it is only defined when x is larger or equal to 0. And then we're curious what's the behavior of the average. As we can see, average is adding up all of the xi and divided by the total number it occurs, which is n. And we're interested in finding the average. So now we already, like previous mathematicians have already found out this formula. So it is actually this bunch of information here, and it's also for all of the x larger or equal to 0. But does this really make sense? So probably we can go through some proof about how we can start from here for each single xi event, and then we can find out the PDF for the average event, xn average. Yeah. Okay, so why is this important? Because when we find out the PDF of the how to say like when we find the PDF of the average of many identically independent distribution, then we can say, well, that's its average distribution. So we can definitely know or get a sense of how its variance be like? Because distribution, remember, a distribution is like it has a shape, and the shape can tell us how varied the values are in that uh in that distribution, right? Okay. So first, we'll give some interesting definitions. So first one is the Sn. So every time you see a U, it's n, because uh in German spelling style, like U and N, they are very, very identical. So so believe me or not, this is n. Okay. All right. So we'll first give some definition. So as we can see, we have not defined a function of like sum it up. We only know that the average is sum it up and then divided by n. But we can define the sum it up by s and the capital Sn to denote it, which is very useful then. And then we can use theorem 7.4 to get a PDF of accent, right? So remember 7.4 is just the it's just like the transformation formula, or you can see, but you can check out whether it's transformation formula or the expect value formula. But based on that theorem, we can find out like xn is equal to 1 minus 1 divided by n times this guy here, and this guy is just Sn. So yeah, it's very easy to see that. So from this point, it's still very easy. And then we'll claim some ideas. So this is probably from previous mathematicians' idea, but it's very hard for anyone to guess out this function, right? Yeah, so you need to make some intuitively thinking, or you need to do some experiments about how to get this kind of value successfully from blank paper. Okay. Uh, and yeah, so, but here we just assume that we know this trend. We just need to prove this is right. So why want to prove this? Because we already see this. So this is what we want to prove. And we just, what's the difference between these two? This is a PDF of the average, and this is a PDF of the sum. So automatically it is not affected by the n. Or we can say it's different from 1n because Sn is equal to the average is equal to Sn divided by n. So we can add by every variable by n or delete it when it's transformed from the Xn to S, from the average to the sum. Okay. All right, so this is the double star, and we want to show this is correct. And what strategy we'll use here? We'll use the mathematical induction. So remember, mathematical induction, if you study before, we usually begin with a base case and then do an inductive case. And base case is the smallest possible one. So that's the beginning stone in the inductive set. So here, we just pick n equal to 2 because when n equal to 1, well, it may not really satisfy because n minus 1, there's no way to calculate its mean or sum because it's just one value. So we start with n equal to 2, and then to prove like this function is satisfied for all n larger or equal to 2 in the natural number scale. All right. So when n equal to 2, we can, then what we'll do is to find out the fs2z, right? And z here, so what is z? Z is not a random variable, but is a realization of the random variable. And s2 here is, yeah, is what we need to find out its distribution form. Okay. And just by theorem 9.5, which is the convolution of function, which is the convolutional formula, when we are dealing with the summation, because z is, you can view z as x1 plus x2, because those are two, because s2 is the sum. S2 is equal to x1 plus x2. So fs2z is equal to, is equal to an integral from negative infinity to positive infinity, and it is two convolutional style. We can view the first random variable realization as x and another as z minus x to separate out, because Yeah, because maybe this y is just z minus x, and x1, z minus x, x2, x, which definitely makes sense. And just remember, like all of the x, x1, x2, x3, they are gamma distribution, which is defined by like they are only defined by when x greater or equal to 0. So next one, we're separating out. So fx1, we definitely know what is xs1. fx1, if we can find it here, so we can just plug the x1 value in to, so here it becomes z minus x times e z times x times the z e to the power of minus z minus x, which is here, which is e to the power of minus x, right? And this is in the range when z minus x is in the range of 0 and greater and positive infinity, and then times another value, and this is will be x2. Because x2 is x, so this one, x times e to the power of negative x, is just this value. So it doesn't change. And this is when x is in the range of 0 to infinity. So this is also what we can deduce from. And then we can do some interesting thing here. We can combine these two, how to say, um, random variables, or maybe not. We can combine these two range, the condition together. And this is when z minus x is non-negative, and this is when x is non-negative. So when we combine these together, we can find an interesting thing, which is like x must be greater than 0 and z must greater than x. And we combine them again, which we can find out is 0 is z greater than x greater than 0. And then we can combine the rest thing together. So z minus x times e to the power of minus x plus, because it's in the power, so the multiplication becomes addition. So this is minus x minus z plus x, which is minus z. So this is what we get. And because now the situation becomes like x is between the value of 0 and z, then we can use 0 and z to be its boundary to do the integration. And then z minus x times e to power negative z will be, yeah, that will be our new answer. That will be our new range, because we no longer deal with negative infinity to infinity for z or for x, but x is just between 0 and z. So we can neglect all of value out, because other values, it's defined, it's well defined, because it's just 0. So it doesn't influence our answers anymore. Okay. And then from this step to this step, it's usually like when we can use the calculator to do that, or we can use a smart calculator. We can use like uh, the calculator that I use is called Symbol app, and Symbol app can do somehow complex it's not very complex, but somehow complex integration. And this range is in the somehow complex. Yeah. Um, that calculator called SimLab cannot do the integration by parts. So if you meet a integration by part question, you may first you yourself first figure out what is u and v, and then like give him the value, like what is u and what is v, and then do the integration by part. So for this part, the result is so this handwriting might be somehow like very difficult to read, but the general idea is like after the integration it becomes e to the power of negative z. So this term times a bracket, and the inside bracket there's z times x squared divided by 2 minus x to the power of 3 divided by 3, and that's our result, right? So it's, yeah, you can see, I don't know where the z comes from, but yeah, this one minus this one. Yeah. So this one minus this one. This is a minus sign. This is a minus sign. And this one here is a time. It's not minus. So it might be confused at first. This is time. This is multiplication. And this is my difference. Okay. And it's go from 0 to z. And we plug in 0. There's no value, because 0 is for x, and 0 times anything is still 0. But if we plug in z, and interesting happens, like this term becomes z times z squared, which is which is z to the power 3, and z to the power 3 minus z to the power 3, but it's 2 over 2 minus over 3, and this becomes 6 under 3 z power 3 minus 6 under 2 z to the power 3. And this, well, finally turns out to be 6 over z, 6 under z to the power 3 times e to the negative, to the power of negative z. Don't forget this term at first, okay? And what's that? What's 6? 6 is 2m minus 1, right? Because n here is 2. So 2m minus 1 is 3, and 3 factorial, what is that? Is 6. So this one is 2m minus 1's factorial. And this one is 2m minus 1. And this is and this term, yeah, is incorrectly spelling, but it's e to the power of negative z. So yeah, so seems like it's correct, right? It's satisfied this process when n is equal to 2. So next one, we are not satisfying only for n equals to 2. We are going to some inductive steps. So now we assume a case. We assume that, so every case, when the number is n, and n satisfy this formula. So we assume this is correct. And then we'll see if n becomes n plus 1, if it's still correct. If that's correct, we prove the inductive case. And combining the inductive case and base case, we can say, well, this conclusion is just as it is. So for the inductive case, we use the theorem 9.5 again, and which is doing the convolutional, because as n plus 1, we can view it as it is equal to Sn plus x n plus 1, right? So we can separate the two random variable out. So first is Sn, and the second is f is x n plus 1. So this is z minus x, and this is x. So roughly idea is this is x, and remaining term is z minus x, but there is still two realization of the random variable they're adding up. So it will be definitely fine. Okay. So yeah, so what's that? Because we assume Sn is already true, we assume this is true, so we can just put this term in. So this become this one. This term become this one. Just replacing what x in this formula, what z in this formula to become x minus z. So there's 1z, there's 2z, and they become z minus x, z minus x. And there's no difference. We still plug in this one. And remember, like this is no longer x, this is z minus x here. Okay. And second term, well, it's not a summations, it's not a summation distribution. It is still the original distribution. So we use this one for here. So the condition will be, yeah, the condition will be x in the range of 0 to infinity. So this is the inductive case step will be where we got. Converting this one to the next one, similar idea. We just timing them together and combining the condition. So the condition doesn't change. It is still like z minus x larger than 0, x larger than 0. So z larger than x larger than 0. So this is the conclusion. This is the condition. And here, we times this term with this term. And we times this term with x term, right? And this term we time with x to the power minus x, which is x power of minus z, and the x term cancel out. And the denominator still keep the same. So we reach this value. And as we done before, because x is in the range of 0 to z, so we just use the 0 to z for the range of this integration. Okay. And here's the magical help. So here, this integration is called complex integration because it cannot be solved by some special organization of the integral. So what we'll use here is we do a integration by parts or partial differentiation. But yeah, both might be work, but I would really doubt whether partial integration works because there's no variable in the denominator. So we'll just use the integration by part. So how we can separate them out? So here, let's say we can depict so we can depict u equal to x, all right? And what's v? V is equal to v is equal to 2n minus 1 factorial with z minus x to the power of 2n minus 1. So this seems like a very easy idea, but it's not. V is dv. So dv is equal to these terms dx. So this is why we pick up the u and dv, the differentiation of v. And you can see, well, where does this term goes? So don't worry, z to the power of minus z doesn't contain x form, so we can treat it as a constant, a coefficient z. And then what's du? So du becomes 1 times dx, right? Because x by differentiation is 1. So du is just dx. And what's v? And v, we need to do the we can do the integration of itself, because this is dv, and we'll do an integration in depth, which is called indefinite integration over it. And we can see it's 2n, because this is 2 power 2n minus 1, so it will increase one of the power again. So increase one, which what is the first one is 2n, right? So it's 2n times 2n minus 1 factorial. And this is v equal to. This is second, this is third, this is fourth. Okay, so this is fifth. This is the fifth one we want to find out. So v is z minus x, because there's minus, so definitely we'll add a minus to that form too. So here becomes the minus term and becomes 2n, right? So that's the v. So that's the fifth term. So this is our integration by part, okay? And what is the remaining one? So we here, and then we can do the integration by part formula, which is called the u v, because it's integral of maybe z to z, 0 to z, and in the form is u dv, right? So this is equal to u v from z 0 to z plus 0 to z v du. Yeah, but don't forget to put a coefficient at the beginning. So you are always times the coefficient here. So that's our result. And you can see here is this term is the v, right? This is v, this is u, this is c. And this is u, right? This is v, this is du, this is c. But he also forget a negative sign here. So that's so this is how we do the integration by part here. Okay. All right, then let's remove all the stuff. Yeah, but I don't really think like this is a calculus course, so I do not really delve that into very detail. Just do the calculator together, and this one is 0. Believe it or not, you can calculate by yourself, but this is 0. Also, why is 0? So when it's z term and z minus z is 0, when it's x term, x here is 0. So it's 0. Okay, and the later term we can use the now we can use the symbol lab to calculate, and we calculate out is this form. So let me check my answer if it's this one too. So yeah, it is the negative of, yeah. So this is a correct one. This is the correct one. And then do from like z minus 0. So when it's z and and z minus z is 0, right? So when it's 0, then plug in 0, what will happen is z to the power of 2n plus 1, and minus term canceled out because there's like it's minus 0 term, and this is another minus sign, so it's canceled. So it becomes this one times e to the power of z. And is this satisfy our answer? Well, it is, because 2n plus 1 is equal to 2 times n plus 1 minus 1. 2 times n plus 1 minus 1. So this one is actually satisfying this formula when we change the n into n plus 1. Yeah, so the inductive case also proves. So this one works. So this one now works. So the only remaining question for now is we want to find out if the summation is that, what about its average? Is the average really this term based on the sum? Well, it's not that difficult for the last step because we can just use the transformation formula again. So we use the transformation formula, we define a function ux, and ux is equal to 1 over n times x. So this is the average. This is a function that takes the value of the sum and then goes to average, right? And its inverse function is n times x. And we just do a first degree differentiation and becomes n. So the first degree differentiation of the inverse function u is n. Okay, and then we apply the transformation formula here. So the distribution of x and x is equal to f as n times x times u, and this will becomes this term, and it will become this term. So this term will become this one. This is because like going from xn to Sn, we times each x with n, because now we do an inverse. We do a inverse from the sum to average. So it's n times x. And then based on the transformation formula, we need to plug in the derivative term as well. So this is n again. So from this one, especially like from this one, if we change every n term into every z term into nz and times z time n in the beginning, so it automatically becomes this one. Just change it from the denotation difference from z to x, and now we're done. So now we're done with this example. So why we're doing this very complex calculation is because we want to find out its average behavior. So now let's move on to the average behavior. Okay. So here, this is the average behavior of the gamma density. So this is gamma density we just calculated out. So this is the formula for Sn. This is the formula for Sn here. 1, 2, 3, 4, 5 with n equal to 1, 2, 3, 9, 16, and 400. So from 16 to 400, there's a big jump. And this is not gamma density. This is a binomial density, as you can see, for when xn equal to 1 and its distribution has two models, right? So it's bimodal density. So what's the trend? As n increases very quick, then the density function become a vertical line heading to 2, which is its mean value. And for this bimodal distribution, it has a very similar behavior as like when n increase very much. So first, there's 2 value, and for n equal to 2, and if you remember the binomial calculation out, like they will combine these two terms to form a center and to form a like another value at center, and this is the most frequent term. So there have 3 value, and then do 4, which means like the 1, 2, 3 each have a different combination. So it's like 1, 1, 1, 1 maybe here, 1, 2 maybe here, 2, 3 maybe here, and 3, 3 maybe here. So it's roughly average out and become more and more like more and more become a like a normal distribution and then become a very, very vertical normal distribution and become a vertical line for n equal to 400 at its mean value. So this is just as what we found for the how to say the weak law of large numbers, because as n increases very much and all of the values should be very close to its mean. So this is correct. But today we'll go from a different approach because we want to find out if we can standardize the variance. Like we're not just satisfied with it's going on. We're not satisfied with it's become a vertical value, but we want the variance to approach a certain shape and it remains there. So can that be happen? So why vertical line is not very useful in study is because when you are doing the statistical inference, like your inference from a sample to population, and if you see a vertical line, there's no idea of how it is lies, how your value lies here or lies here. But if you can see for this shape, when you are finding like, well, my average in the sample is here, then you can see, well, it is not very reasonable because roughly the value should be in this region. So this is why we do the statistical inference. So from a statistician's view, we want to stabilize the variance as it's increasing. So now we'll figure out its increasing rate so we can determine it. So that's the idea. So as you can see, the expected value of the variance equal to mean is equal to the population mean. And this is a sample mean. This is a population mean, right? This is the average of the sample mean. Okay, this is the average. The expected of a sample mean is equal to the population mean for when n increases. But variance has a different story to tell because variance is x and variance of the like the average is equal to the variance of this term. And this is a single value for each random variable. So each of the variable itself have a variance of sigma squared, right? But we divide it by this one. What will happen is like this is when we do the variance, this will be squared. So this is like n to the power of 2 under 1, right? And this one times this one. Well, this one here is sigma squared. But because they're independent, IDD distribution. So this is just n times the sigma squared. So it becomes this one because the only one term n cancel with one of the n in its denominator. And so there's still one n remaining in the denominator. So it's sigma squared divided by n. And this one will approach to 0 as n goes to infinity. Does that make sense? Yeah, because sigma squared is a fixed value if it's not infinite. So if it's not infinite, this is fixed value, and n is not a fixed value. And n, what is n? N is a variant value. N increases infinity. So this go to infinity, this is fixed, which is 0 in the end. Okay. And so, but after we figure that term out, we may think, well, if we do if we time as some kind of like a constant or coefficient, we may change this property to 0 if we can just convert this term into sigma squared. So some people might already realize that if we time a root square of n here, and this term will become this term will become like n to the power of -1/2. And this is n to the power of -1 after square, right? But that's not really an idea. That's not really a correct idea because n to the power of 1 negative power of -1/2, when squared, it will become n to the power of 1/4. So it's still not n. So yeah, so it's a hard way to tell. But another way to do it is we can pick a parameter here, and this parameter we'll find out is the alpha, and alpha times the average minus mean, the individual mean, this one, and we want this one to be stable. And you can see, so first one we picked alpha equal to n to the power of 1/4, and the result is goes as it increases to 100, it still become closer and closer to the vertical line. And with the root square of n, then it stabilizes at the end. So you can see here is it's very like a uniform distribution, right? So this is what we want. And if alpha is equal to n, and what happened? Just as I said, it increases too large, it increases too much, or n, or this becomes n to the power 2 divided by n. So it vanishes out. It becomes infinity. The variance becomes infinity. Okay. So in the previous slide, which is slide here, you can remember this graph, and only in the middle column, the alpha equal to root square n settles, make the density function to settle down into a roughly symmetric and bell-shaped distribution. So the graph at the previous slide showed that as it increases, the root square of n seems to be standardized and stabilizes density. So this makes sense. So why this makes sense is because the variance of alpha times this value and this value, the alpha of this one, it's just the how to say, the sigma square divided by n. And we time alpha here, which is alpha, and the variance will make it square. So it makes this square too. So if you want to become a sigma square in the end too, and then we'll choose alpha to be root square of n. So this will be n, can cancel out with this one. So this brings us to our central limit theorem. So now we know what is the alpha here. Alpha is root square of n. Okay, so central limit theorem states like that. So let x1, x2 to xn. So there's n independent and identically distributed random variables there with finite mean and finite variance as sigma squared. So if they are infinite mean, infinite variance, we are not able to figure out because this behavior here doesn't satisfy, and we are in a undefined situation. Okay, so for all of the n larger or equal to 1, we can define this one to be this one, as we defined before, right? We can define by the average divided by n. Okay, and z is the distribution. Zn is the distribution, which is the root square of n, the alpha term we find out, times the difference divided by its standard deviation, which is sigma. So this is central limit theorem. And then for any real number a, it has a property that the limit when n approaches infinity, like the distribution is equal to phi a, and phi is a city of the standard normal distribution, which is n10, and this one is very, very easy to figure out. We already have a table in a long history to figure out what the percentage of it, what goes to which value. So this one is called a z-score. This one is also called a z-score. So if we can know a z-score of that, we can convert it to the CDF of Zn to figure it out. So this is the central limit theorem. So this is roughly used the idea we find here is the root square of n can stabilize its CDF. And what we can say about it. So Zn is converged to the distribution function, standard normal distribution. So this is what we know the core idea of the central limit theorem. So know that, and then we can use another way to depict it. This can be viewed as xn average minus the expected value of xn average divided by root square of variance of xn average. So why that makes sense? So let me explain here. So first step, from this one to this one, or to show from this one, the first step might be we can divide it by root square of n from the top to the center, right? So we can use this one. Because since this is divided out, so let's think about it. If it's divided out, then this one divided this one, and this one will also divide it to. So it becomes this term. And what this term becomes is like, yeah, this is still xn average. And the mu is just, as we know before, we know from the weak-lob Blanche number, this is expected value of the average when n goes to infinity, right? When n becomes very large. So this can be converted. And here is still sigma divided by root square of n. And what we can find out here is like, this is equal to xn average minus the expected value of xn. And this is divided by, well, this is divided by the large square of sigma square divided by n. And this one, what is this one? This one is the variance of the, this is the variance of the average random variable. So yeah, so if we plug this one into this one, we get this one already. So now we are done with it. Okay. So you may say, why this is the variance of it? You can inference from previous pages, and we have already just talked about that. Or you can find the page, I think it's here. Yeah, so here, you know, this, the variance of the average random variable is equal to this term. Okay, so that's how we find it. And now we can use the central limit theorem to do some very, very positive and useful thing. So central limit theorem, which means like the density of it with sample size n. The dotted line here is the standard normal distribution. So when n increases from 1 to 4, 16 to 100, it becomes very, very closer and closer to it. Okay. And this means like this phenomenon occurs for any distribution with finite mean and finite variance. So this is actually not only for gamma, not only for bimodal, not only for binomial, but for any distribution that that you can define for any PDF, or that you can find or prove any function which is a PDF. You always have this property. So let's see two examples in the end. So first example is crossing the is to calculate what's the probability of some values exceeds a certain value. So consider a simple random variable of n equal to 500 gamma distributed random variables. Okay, so this is 500. It's a very large number. Maybe not large enough, but in this context, it's large enough to calculate, because for central limit theorem, we usually need at least 40. Okay, sometimes we'll say at least 30. So make more confidence, we can say at least 40 is a large number. So 500 is a very, very large number. So satisfy it. So what's the probability that a sample average actually exceeds the mean equal to 2 by 0.02? So this means like we want to find the average of xn is larger or equal to 2.02 by 2 plus 0.02. And in some traditional thinking, well, we probably found it's the density function, is the probability density function that goes from 2.06 to infinity. This is our original way to find out. But gamma distribution, as we see before, gamma is very complex. Gamma is a formula like that. So it becomes very complex when calculate this formula. But with the help of the central limit theorem, we can use this one. We can use the probability of the xn minus mu larger or equal to 2.06 minus mu. And this one we just use, well, yeah, we just use the formula in this form. We use the formula in this form. And I think this form, this blue one, is the most useful one in later works. So after we apply that form, what happens like, well, we can figure out this term, right? And you can calculate the variance. The variance and standard deviation is root square of 2 divided by the root square of n, which is 500. And we can find what we left to find out this form. And this one becomes the probability of xn minus 2 larger or equal to 0.95. Because this term you can calculate by calculator, and this is close to 0.95. And just by central limit theorem, this one is very close to a standardized normal distribution. So we can use a z-score to calculate. So what is z-score greater than 0.95, right? By central limit theorem is 1 larger than that is 1 minus the term, which is smaller or equal to 0.95. And 0.95 is not even one standard deviation away from the mean. So it still has some value. So by calculation is 17.11, something like that. And another example, the last example is the rounding to a nearest integer. So suppose an accountant wants to simplify his bookkeeping by rounding down accounts to nearest integer. So it's always rounding down, it's not rounding up. So when you met a number like 100.99, it goes to 100, not 101. Okay, so this is the process. And what's the probability that the cumulative rounding error of 100 transition exists $10. 100 transaction exceeds $10, which means like, well, it is really possible. Because every time you have maximum of 1 and 100, which means you have a maximum amount of rounding $100 for yourself, all right? Which is a one way to make you rich to do the job bookkeeper. Okay. So what's the x1, x2, x100 here? So there's 100 transactions. So there's 100 IID. IID distribution is a uniform distribution. So this is because like for example, this is 100, this is 101 for the value, and it has every value, any value can happen in between, and you all goes them to 100. So it is very uniform distributed from -1 to 0. Because if the value is here, very close here, then the loss is -1. If it's here, then it's 0. So this is the rounding situation, how the rounding works. Okay, so we can use the central limit theorem here again. So it's x1 plus something plus x100. Just sum it up, smaller than 10, smaller than -10, or larger than 10. If we count this one as 1 to, it's 0 to 1 uniform, right? This is the same idea. And this is equal to the probability of average smaller than 1/10. And this is used the idea of like, this is used the idea of is equal to n under Sn. And here alternative way is like, if it's a uniform of 0 to 1, as you count it as the rounding is always a positive value, and this will be larger than 10. Okay, so this is what we depict here. And then we apply the central limit theorem to it. So minus the average. Average is always in uniform distribution, so it's -1/2. And the standard deviation is the root square of 1/12. So we plug this value in. we can figure out this term first. So this term is roughly 8 times root square 3. And this is the z-score. This is the z-score by central limit theorem. So what's the z-score of mine is smaller or equal to 8 times root square 3. So we can draw a picture to show you how it looks like. So this is 0, this is 1, this is 2, this is 3, this is -1, this is -2, this is -3. And usually a normal distribution is flat, right? This is a normal distribution and maybe even closer. So yeah. So the normal distribution is close to 0 and then picked up to, yeah, this is normal distribution, right? And what's 8 times root square 3? So if 8 is here, then 8 times root square 3 is here. Now we're calculating the possibility that is smaller than this value. So it's nearly all of the area is smaller than this. So it's closer to 1. So absolutely, if you are a very smart bookkeeper that round your account, every account to the closest, the lower integer, and you will make great money because every 100 transaction you at least earn $10 by the central limit theorem. So thank you very much for this one, and have a good holiday. And maybe I'll meet you in the winter if you like. If you like to continue for more complex probability problem again.